everybody. This is the fourth session of the mini course on multiplicity theory and ideals of König type. In the third lecture, we had a theorem which gave us a nice criterion for the Cohen-Macaulayness of standard graded positively graded K-algebras in terms of the multiplicity. So whenever we have a ring S mod I, a positively graded ring, where here S is just a polynomial ring, over the field K, and I is an ideal in S, then by this theorem that we proved yesterday, we know that R is if F1 to Fd be a system of parameters, indeed a homogeneous system of parameters of R, then we know that R is Cohen-Macaulay if and only if the multiplicity of R is just equal to multiplicity of R divided by this ideal generated by F1 to Fd. So, if SOP, here I consider the degree of Fi to be 1, because if you remember, if the degree of Fi was Ai, here we had A1 times Ad times multiplicity of R. So if all these degrees are 1, then a Cohen-Macaulayness is just equivalent to say that these two multiplicities are equal. What we are going to do today is to consider this equivalence and study Cohen-Macaulay property for such rings such that our ideal is either a monomial ideal or a binomial ideal, and looking for systems of parameters of linear forms with this property, such that whenever we construct this ring, then it gives me a nice structure such that I can say something about multiplicity like this number does not depend on the characteristic of the base field, because in general this is not the case. In general, we know that Cohen-Macaulayness of this ring depends on the characteristic of the base field. Even in if I is just a square-free monomial ideal of degree 2, I mean the very simple case that we can imagine for I is when I is just the edge ideal of a graph G. Even in this case, the Cohen-Macaulayness of S mod Ig may depend on the characteristic of the base field. There are examples of graphs such that when the characteristic changes, this property may hold or not hold. So we are interested in families of ideals such that Cohen-Macaulay property is independent of the base field K, and we want to somehow use this criterion and look at the multiplicity, what happens for the Hilbert series of the ideals we want to consider. What I'm going to say today is from two papers that I will write down here, the references of my today talk are these mainly parts of these two papers. The first one is Title is Systems of Parameters. And Cohen-Macaulay property. And the second one, by Herzog, E.B. and I. Graded ideals of König type. You can find both papers in archive. So I discuss some parts of these papers which are related to what we discussed. I mean about multiplicity. And I'm not going to, like the first 3 lectures, to give in detail all the proofs, because in one session I cannot do it. I mean, because I don't have much time. So some parts I do with detailed proof, and some parts I just mention the main idea. But you can see the precise proofs in these 2 papers. Okay, as I told you, we consider monomial ideals and binomial ideals. Let me first remind you the definitions. Whenever I write S, so wrote this lecture, I mean a polynomial ring. Over a field K. It indeterminates x1 to xn. By a monomial in S, we mean an element of the form x to the a, which I mean x1 to a1 up to xn to an, where here by a I mean the vector a1 to an. Such an element in S is called a monomial. And a monomial ideal is an ideal in S which is generated by a family of monomials. So a monomial ideal, or let's say an ideal I in S, is called a monomial ideal. For short, I just write mon. If it is generated by monomials. In fact, it is not so hard to see that when we have a monomial ideal, there are finitely many monomials which generate I. And if we consider minimal sets of this form, minimal with respect to inclusion, this set is unique. So we show this set by GI. So by GI, I mean the unique set of minimal monomial generators of I. As I told you, this is a finite set because We are in a Noetherian ring, so anyway, I is finitely generated. So I is generated by finite number of polynomials. But the point is that when we have a polynomial in I, which I itself is a monomial ideal, all the monomial parts, which we call them the elements in the support. So if f is a polynomial in general in S, then let's say f be equal to sigma Ra x to the a, where this Ra comes from the field, and we have finitely many of them. Then by support of f, we mean just these monomials such that they appear with non-zero coefficients. So the point about monomial ideal is that when f is in I, all the elements in the support also belong to I. So these finitely many polynomials that generate I give us, in fact, a set of generators of monomial, which comes from the supports. These things also generate our ideal, and this is a finite set. And why this the minimal one is unique is also not hard to prove. Now let's define a binomial ideal, because these are two classes that we are going to consider and study their quotient ring. So any element of the form u minus v in S is called a binomial whenever u and v are monomials. In S. And what is a binomial ideal? In our setting, by a binomial ideal, we mean an ideal which is either is generated by binomials or monomials. Okay? So an ideal I in S is called a binomial ideal if it is generated either by monomials or binomials. So in our setting, in particular, any monomial ideal is a binomial ideal. Okay. So in the literature, maybe you can find the definition of binomial ideal just generated only by binomials. But also in some context, you can see that also this kind of ideals, which the generating set is a mixture of monomials and binomials, also called binomial ideals. So for the convenience of just writing down our statements, that each time we don't repeat either a monomial ideal or a binomial ideal, we just consider all of ideals of this form all as binomial ideals. So what we are interested in is that we consider, as I told you, the ring S over I when I is a binomial ideal. As we saw in this criterion of Cohen-Macaulayness in terms of the multiplicity, we saw that the existence of a nice system of parameters is important for us. A nice system of parameters such that makes this equality of multiplicities valid. Now we are looking for, our next goal is to define a nice class of system of parameters. And we applied them, we studied them in such rings. So let D be the dimension of our ring R, which is S mod I. This can be defined in general. No matter if I is a binomial ideal or any ideal in S, where R is I is just a graded ideal in S. A system of parameters f1 up to fd of R we call a special system of parameters. Whenever each fi is either a variable x, x r, or is of the form the difference of two variables, like xr minus xj, say. Okay? So any special system of parameters is the elements are of this form, either variables or difference of variables. A very simple form. What we are going to do is that to consider binomial ideals which admit such system of parameters and study their multiplicity and investigate if this tells us something about Cohen-Macaulayness or not. So this is the statement of this theorem. Let R be just S mod I, where I is a graded binomial ideal. And let S mod I, or just simply say R, admits a special system of parameters. And then we want to show that the Cohen-Macaulay property of R is independent of the base field. This means that if it is Cohen-Macaulay over some field, then it is Cohen-Macaulay over all fields. Okay? By this criterion that I wrote at the beginning, we are interested to look at the multiplicities. Of course, computing the multiplicity is not an easy job, and also the Hilbert series in general. But maybe we get some information of it with these conditions. So I consider this nice system of parameters by, first of all, let D be the dimension of our ring, and let F1 up to Fd be elements in the polynomial ring such that the corresponding elements in S mod I be a special system of parameters. Of R. Okay. I consider L to be the ideal generated by F1 to Fd. And then we are interested in this equality. We want to consider multiplicity of R mod L and multiplicity of R, as I told you, because this system of parameters is special. All these Fi's have degree 1. So we just should consider this condition that this multiplicity is equal to the multiplicity of R to have the Cohen-Macaulay property. Okay? So this is why I want to consider the ring R divided by L. So R is just, this is just F1 times Fd R, where R is S mod I. So this is isomorphic to S divided by I plus F1 to Fd. And this is isomorphic to S divided by F1 to Fd. This ideal divided by F1 to Fd. But F1 to Fd, we know that any of them is either a variable or difference of two variables. And this makes our job easy, because then this, what is this quotient ring? We have a polynomial ring that either we remove some variable from S or we identify two variables, right? Because if, for example, F1 is just a variable and I divide S by F1, this simply just means that I have a polynomial ring in less variables. I mean, we just remove this variable F1. And if I have some Fi to be of the form xr minus xs, when I divide S by this polynomial, it simply means that I replace xs by xr in the polynomial ring S. So what we have is that S divided by F1 up to Fd is just isomorphic to T, where T is again a polynomial ring. And the same with, if now we consider the corresponding ideal of this in the polynomial ring T, it's just, again, simply means that we do the same in the ideal I. So I call this new ideal in T, which corresponds to this ideal, to this ideal, I call it J. So I will have R mod L is isomorphic to T divided by J, where J is an ideal obtained from I. By just putting 0 in any monomial. Or say in any generator. Okay, in any generator, a minimal generator of I, by putting 0 for FIs which are variables, and identifying also some variables depending on the elements Fi. What I mean here is that, for example, if in the ideal I have, for example, x1, x3 minus x2, x4, for example, and let's say another term, x1, x3 to the 5, I don't know, minus x6. And if I have, for example, among the elements in the SOP, I have Fi to be, for example, x3 minus x1, what we do here is just replace x3 by x1. So what I get is here is that just x1 squared minus x2, x4, right? And if among my Fi's I have, for example, x6 only, here I just put x6 to be 0. So what I get here is just, again, if I replace x3 by x1, then I have x1 to the power 6, right? So we do this replacement in the ideal I to get our new ideal J with these generators. As you can see also from this example, when I have a binomial or monomial and I do these replacements, again I will get either a binomial and sometimes even from the binomial a monomial. So anyway, in my new ideal, the generators again are of the form either monomials or binomials. Okay, then we know that J is again a binomial ideal as well. So as we said, we know that R is Cohen-Macaulay if and only if multiplicity of R mod L is just multiplicity of R. But instead of R mod L, we can consider T mod J. So this is equivalent to say that multiplicity of T mod J is equal to multiplicity of, and R is just S mod I. Okay? So R being Cohen-Macaulay is equivalent to say that multiplicity of these two rings are equal. But both of these rings have the same structure, polynomial ring divided by a binomial ideal. And in lecture 1, we saw that we can read multiplicity from the Hilbert series. We just look at, for example, the nominator in the fraction that explains the Hilbert series and the value of nominator at 1. So let's consider the Hilbert series. If the Hilbert series of these two rings are independent of the base field, this means that the multiplicities also are independent of the base field. And when these two numbers are independent, then Cohen-Macaulay property also has the same situation. Okay? We know that the Hilbert series of, okay, I didn't mention this result, but I mean, this is a standard result about Hilbert series, that the Hilbert series of an ideal and its initial ideal are the same. So the same for T divided by J. But the point is that I mean, does the initial ideal depend on the base field or not? We know that the initial ideal can be computed by a Grubner basis. I mean, if we find a Grubner basis for the ideal I, then the initial terms of these elements generate initial of I. But in our special case, when an ideal is a binomial ideal, either I or J, then being a Grubner basis for a set is independent of the base field. Why? I don't go through the details, but I explain you because, okay, by Buchberger algorithm, we know that whenever we have a generating set, say G1 up to Gm, if this is a generating set of or ideal I, okay, generate, then by Buchberger algorithm, we know that we can get out of this by computing the S polynomials, and each time adding the remainder to this set, we can get a Grubner basis for our ideal. But this procedure of computing these S polynomials and getting the remainder each time to get the Grubner basis, whenever these GIs are of the form U minus V, or simply just a monomial U, if you just look at the definition of the S polynomial, for two polynomials, you can easily see that when our polynomials are of this form, this computation has nothing to do with the field K. Okay? It just depends on these monomials that appear. So getting a Grubner basis, this process does not depend on the base field. This means that these initials can be computed no matter what is the field K. They are always one constant ideal corresponding to I or to J. So it is enough we just look at these initials, and we know that these initials are monomial ideals. And for monomial ideals, we know that the Hilbert, if let's say I give it a different name, I don't know, if P is a monomial ideal, P usually is used for prime, so I just call it Q. Then the Hilbert function of S divided by Q is just, the cardinality of, we just consider the monomials in S, which does not appear in Q, and they are of degree n. So we just count some basis elements that only depend on the generators of our monomial ideal Q. So these two Hilbert series are completely independent of the base field. So the whole thing means that these two numbers are independent of K, and we get what we want. This situation holds also for Cohen-Macaulayness. Okay? So what is our next goal now that we know this special system of parameters are somehow nice because and gives us this information about Cohen-Macaulay property? We are interested to see, at least for whenever we have a monomial ideal or a binomial ideal, for which classes we have such a nice system of parameters. Okay? The simplest class that we can start with is just the edge ideals of the graphs, or square-free monomial ideals of degree 2. I changed a little bit the order of the material I want to say, because first we started with the edge ideals of graphs. We noticed that exactly those edge ideals have this nice system of parameters who correspond to König graphs. So this was where König concept showed itself. And then we try to extend this to any graded ideal. So came the definition of graded ideals of König type. So the reason that we discuss ideals of König type comes from, in fact, the edge ideal of graphs, because they are exactly equivalent to the existence of such a special system of parameters. So let me remind you what is, now we go to the world of combinatorics. I remind you some definitions. Some of you for sure know these concepts, but for those who are not familiar with concepts in graph theory, we consider G to be a graph. I always show the vertex set of this graph by VG and the edge set by EG. By a matching in the graph G, we mean a subset of the edge set, so it contains some edges of the graph. I denoted by capital M, is a subset of the H set, such that for any two edges in M, I mean two distinct, of course, distinct edges in M, the intersection be empty. So a matching is simply just a subset of the H set, which are, these edges are pairwise disjoint. For example, in the graph, in the 5-cycle graph, this edge and this edge form a matching of the graph because they are disjoint. But if I add this edge to it, then this is not anymore a matching. Another concept that we are needed to define König graphs is the vertex cover of a graph. What is a vertex cover? It's just a subset of the vertex set. If it intersects all the edges of the graph. Okay? Somehow we say that it covers all the edges. This is what we call it vertex cover. So it covers all the edges. Again, let's come back to this graph. Here, for example, if I consider these three vertices, so I mean the set 1, 3, 4, this is a vertex cover because each edge of the graph has at least one vertex in this set. Okay? And a vertex cover which is minimal with respect to inclusion among all the vertex cover is called a minimal vertex cover. So this means that no proper subset of this set is a vertex cover anymore. So the minimum possible one. Of course, the minimal one is not unique. Maybe we have a couple of minimal vertex cover, even of different cardinality. But we consider the minimum number, the minimum of all this cardinality of the minimal vertex cover. We call it, we denote it by tau g. So I define two invariants, mg, which I call it the matching number of g. This is just the maximum cardinality of matchings of G. And I denote by tau G, we call this the vertex cover number. This is just the minimum cardinality of vertex covers of G. Okay? For example, in this 5 cycle that we considered before, if you remember, we had a matching of cardinality 2, and we say that if we add another edge, then this is not anymore. There is some question there. Make the soft copy of this course available. Okay, yeah, this course is recorded and later is put on YouTube, so don't worry. So the matching number is just 2 because we couldn't add another edge and make a bigger matching. And also the vertex cover number. So far we know that we have a vertex cover of cardinality 3, but can we make it less? I mean, do we have a vertex cover of cardinality 2? This is not possible. You can check. I mean, if I remove 3, then it makes a problem because then the edge 2, 3 is not covered by any element in the vertex cover by just 1 and 4. So 3 should be here. And also the same with 1 and 4. And if you check other things, for example, if you just choose 2 and 5, you see that you need either 3 or 4 also. So here, vertex cover number is 3. Okay? An easy observation is that always tau of G is greater than or equal to M of G. Why? Because by definition, what is tau of G? The minimum cardinality of vertex covers. So there should be a vertex cover with this cardinality. But any vertex cover by definition should cover all the edges of the graph. Among these edges, we have the edges that come from the matching. So if I have a matching in the graph, which the number of these edges is just mg, at least one endpoint of each of them should belong to our vertex cover. So from this edge, I should have at least one vertex in my vertex cover. One vertex from here at least, one vertex from here at least, and so on. So any vertex cover C which I consider should have at least mg vertices inside, which comes from this, the one endpoint of these edges. And this is just tau G. I mean, I consider the vertex cover which gives me the vertex cover number. So it can be easily seen that this is always true. But the other way around is not true. You can see from this example. Here tau G was 3 and mg was 2. So most of the time the inequality is strict. Okay. Okay, we say that most of the time this is strict inequality, but a famous theorem by König and very old from 1931 König proved that whenever G is a bipartite graph, then we have equality. So this is a family with these two numbers are equal. But of course, it is easy to find some graphs that are not bipartite, but still this equality is valid. For example, just simply look at this graph. I connect another vertex to here. Okay. And then the matching number, okay, I choose these 3 edges. They are pairwise disjoint, so the matching number is 3. The vertex cover number, by this inequality, I know that it should be at least 3. So if I find something which is exactly 3, then this is just a minimal vertex cover. Consider these 3 vertices. If you check, all the edges are covered by this, by the set 2, 3, and 5. So this is a vertex cover. And it is of minimum cardinality because we know that this number should be at least 3. And this graph is not bipartite because it has the odd cycle C5. So then come the concept of König graph, which covers all the graphs with this equality. This is exactly the definition of a König graph. Okay, so from König's theorem, we know that already the set of bipartite graphs are contained in the set of König graphs. So this is the concept of a König graph. And as I told you, whenever we look at the family of edge ideals, so let's see the definition of edge ideals too. When we look at this family of ideals, then precisely for edge ideals of König graphs, we have these nice special systems of parameters. So let G be a graph with the vertex set, I call it just N. The edge ideal of G is the monomial ideal generated by those xi, xj, such that I and j is an edge in G. And this is an ideal in the polynomial ring kx1, xn, where these are indeterminates and k is a field. Okay? So the reason that these graphs show themselves is that they are precisely those edge ideals which have this nice property that the ring S mod Ig has a special SOP. So I'm not going to say the proof for S mod Ig because we have it in a more general frame. Whenever I is any monomial ideal of König type, and these two things are equivalent. Okay, then as a corollary, we get it for the edge ideals. No questions so far. Okay. We can have our break. No. Yeah, we can have a break for 10 minutes. As I told you, our goal is to extend the concept of edge ideal of König graph to graded ideals, which we call them graded ideals of König type. So let's see what are the algebraic description for these two numbers matching number and vertex cover number, which define König graphs. This is an easy lemma, which I'm not going to prove, but I explain a little bit. Whenever we have a graph, then the edge ideal of G is just the intersection of those prime ideals which are generated by variables xi1, say xir, such that the set, I consider G to be a graph on N, and then this I1 up to IR is just a minimal vertex cover of G. Minimal vertex cover of G. Okay, so the minimal vertex covers of G are in one-to-one correspondence to the minimal prime ideals of the edge ideal. From the definition of edge ideal, this is not hard to see. This means that height of IG is the minimum of cardinality of such sets, which is exactly the vertex cover number by definition. So as a simple corollary, we know that height of IG is just tau G. And what is the algebraic description for the matching number? Okay, we say that a matching means that we have a set of edges which are pairwise disjoint. If we consider the monomial corresponding to these edges, for example, I don't know here. If I consider the monomial, I mean the monomial in the edge ideal, this is an element in IG. And x4, x5 is a monomial in IG, in fact a minimal generator. Whenever these two things are disjoint, these two monomials form a regular sequence because they don't have any variable in common. So what is the matching number? It's just the maximum length of a regular sequence of monomials in or ideal IG. Okay? Because we have, whenever we have a regular sequence of monomial in IG, we can have a regular sequence of the same length coming from just the minimal generators. So here either I can write among the minimal generators or not. So to look at the concept of being a König graph in algebraic term, we can say that the height of the ideal should be this number. Or in other words, if the height is h, there exists a regular sequence f1 to fh of monomials in IG. We call this number, we denote this number by m grade. M stands for monomial, so we call it a monomial, not graded grade, the monomial grade of IG. So we only consider those sequences which are, contains monomials. And in general, we know that M grade, of course, is less than or equal to, for any ideal, we can define it, is less than or equal to grade. And because we are in a polynomial, this grade is just height. So in general, m grade is less than or equal to height. But whenever this happens, which in the case of edge ideal just means that these two numbers are equal, we called it a König graph. So let's see the definition in a more general frame. As usual, S is just a polynomial ring. And I in S, suppose that this is a graded ideal. And let's say height of I be H. We say that I is an ideal of König type. If there exists a sequence f1 up to fh, so the length of this sequence is exactly the height of our ideal. In I, which is part of a minimal generating set of I. And secondly, their initials form a regular sequence. So we fix an order. We fix a monomial order, and we say that I is an ideal of König type with respect to this order. So here, this is just a monomial order. Okay? So we should have two conditions. First of all, this f1 to fh should be part of a minimal generating set of I, and secondly, their initial should form a regular sequence of monomials. Whenever our ideal is from beginning a monomial ideal, because the initial is just the, we can choose these things to be just monomial, and the initial is just the monomial itself. Okay? So obviously this generalizes the concept of edge ideal of a König graph because it's a monomial ideal. So it's equivalent to say that we have edges E1 up to EH, where H here is just the tau of G when we translate it for the edge ideal. And whenever we say that this sequence is a regular sequence, this just means that these two edges are pairwise disjoint, which means that they form a maximal matching of the graph. So this is how we extend the definition to any graded ideal. Let's see an easy example. I consider an ideal, a binomial ideal, let's say, for example, okay. So I is generated by two polynomials. I call them f1 and f2. And I consider the lex order of course, the definition, as you see, depends on our order, because the order obtains the initial and this sequence to be regular or not. So I consider the Lex order induced by x1 greater than up to x4. Then with this order, initial of f1 is just x1 squared, and the initial of f2 is just x4, x5. And you can see that the initials form a regular sequence. So this means that, first of all, f1 and f2 is a Grosvenor basis for I. So initial of I is just generated by x1 squared and x4, x5. And the height of our ideal, which is just the height of the initial, is 2. So all the conditions of the definition hold, you see. The initials form a regular sequence because they have no variable in common. And f1 and f2 is just not only part of minimal generating system, but a minimal generating system because height is 2. So I is of König type with respect to this order. So in this way, we can construct a lot of examples just to, whenever the initials are pairwise coprime, we always have this situation. As I told you, when we look at the edge ideals of graphs, and we are looking for those graphs such that we have a special system of parameters for S mod IG, we come up with König graphs. Now we want to see that, is it the same when we consider ideals of König type or not? Whenever I is a monomial ideal, this is in fact the case. But in general, in a natural way, we can associate a sequence to any graded ideal of König type, which is capable to be a special system of parameters. Let's see what is this sequence. So let, in general, I be a graded ideal. Of König type. With respect to some order. And suppose that this sequence that in the definition, if you remember, there should be some sequence f1 up to fd, say fh, to keep the same notation. The condition was that the monomials ui, if I put ui to be the initial of fi, this should be a regular sequence. Where here by ui, I mean the initial of fi for all I. Okay. This we have by the definition of being of König type. Now, we attach to this ideal a sequence in a natural way. We consider for each I bi to be just the support of ui. By the support of a monomial, I mean, okay, let me mute because, okay. Those variables that divide ui. So for any I between 1 and h, we consider bi to be the support of ui, and we consider the set A to be just the complement of union of bi's. What is n? N is just a number of our variables. I mean, this I is an ideal in the polynomial ring k x1 up to xn. Okay? Then, first of all, because u1 to uh form a regular sequence, this means that these bi's are pairwise disjoint. So, and obviously, because A is defined in this form, A is also disjoint from each of bi's. This means that n is just equal to cardinality of A plus sum of cardinality of bi's. Okay? Now, for each I consider Ci. Okay, before introducing Ci, let J sub I be the minimal index such that xji belongs to bi. Okay? And we consider Ci to be the set of all xr minus xji such that r is different from ji and xr belongs to bi. Okay? We will see this structure in a simple example. So for any I between 1 and h, we consider this Ci. So what is the cardinality of Ci? Simply cardinality of bi minus 1. And then if in this equality I replace this cardinality, what I get is that n is equal to plus cardinality of Ci minus h. So this cardinality is just n minus h. So if I consider just the set C to be a union with C1 up to CH, which is the cardinality of, the cardinality of C is just this one. And then C is of cardinality n minus h, which is, if you remember, h was the height of our ideal. So this is just the dimension of our ring S mod I, which we call it D. Okay? So this sequence has the right length, this set, the elements in this set as a sequence has the right length to be a system of parameters because its cardinality is just the dimension of our ring. This is why we call it a potential system of parameters for the ring S mod I. Okay? For example, if I have, I don't write down what are FIs. If I just have UIs, which are the initial of FIs, I can get this sequence. For example, if I have x1, UIs are monomials, so I write down just some monomials. And if you remember, these monomials should form a regular sequence, so they should be coprime. I don't know. So let this be U1, U2, U3. And our polynomial ring be just K of x1 up to x6. Okay, so we have 6 variables. What we do by what we introduced, here the support of U1 is just x1 and x3. So the element that we consider is just x3 minus x1, because this the minimal index that appeared here is 1. So this is the sequence attached to U1. Let me make it bigger, so maybe we have, I put it 7. So here I have x4 minus x2 and x7 minus x2. And corresponding to x5 squared, I have nothing, because I don't have, other than this minimal one, I have nothing. And I should also put a variable which does not appear here. If you see, x6 is not among the support of this monomial, so x6 also an element here. So altogether, I have 4 elements in the potential SOP. Dimension of my ring is 7. So dimension of S mod I is just 7 minus, this is the height of our ideal, which is 3. This is 4. And this is a sequence of length 4. So the length is fine to be a system of parameters. But of course, this is not enough. We should show that when we divide by this sequence, we get a 0-dimensional ring, which is not always the case. But good news is that whenever we have a monomial ideal, this is indeed a special system of parameters. Okay, from now on, I have to just mention the statements of some results, because really in one session, I'm not able to say everything with details. So I just write the statement of this theorem for monomial ideals. Let I be a monomial ideal. Then the following statements are equivalent. I is of König type. And S mod I admits a special system of parameters. And what is the special system of parameters in this case? Precisely the system of parameters that we construct in this form, that we call it potential. I mean, this potential one, in the case of monomial ideals, is in fact really a system of parameters. So in particular, whenever I have the edge ideal of a graph G, IG is of König type simply means that G is a König graph. And this is equivalent to say that we have a special system of parameters. Okay? You can see the proof of this theorem in the first paper that I gave in the references. I gave you 2 papers. In the first one, you can see a proof of this theorem, really written in detail. So, as a corollary, if you remember this, at the beginning of this session, we proved a theorem that say that whenever we have a binomial ideal which admits a special system of parameters, then the Cohen-Macaulay property of S mod I does not depend on the base field. And now we have all the needed situation. Whenever we have a monomial ideal, this is included in the family of binomial ideals. So if it is of König type, then we are sure that the special system of parameters exists. This means that we can apply the theorem and say that the Cohen-Macaulay property of such rings are independent of the base field. So let I be a monomial ideal of König type. By what I explained, the Cohen-Macaulay property of S mod I does not depend on the base field, or more precisely on the characteristic of the base field. Okay, so just combine this theorem with the theorem that I proved at the beginning of this lecture. We get this corollary. So in particular, when we have the edge ideal of a König graph, this situation holds. Of course, for the edge ideal of the graphs, this was known already because in this case, there is a combinatorial description for edge ideal to be Cohen-Macaulay. It is shown that it is equivalent to be pure shellable or pure vertex decomposable. So whenever we have a combinatorial description, automatically this holds. But this more general case for monomial ideals, of course, is a much bigger class. And in the same paper that I mentioned, in the references that I gave you, in fact, we give a characterization for the Cohen-Macaulay property of S mod I in terms of the unmixedness of some ideals attached to I. So if you are interested, you can see also this result in the first paper, that what are the equivalent conditions. And from this description also you can see that it does not depend, this Cohen-Macaulay property does not depend on the base field. Okay. Another nice corollary that we can get is that okay, let me give you a very easy exercise. Whenever I is a graded ideal of König type, let's say with respect to the order, some order, then initial of I is also of König type. Okay, just simply use the definition. Then another corollary of this corollary would be let I be an ideal of König type. Any graded ideal. And then the Cohen-Macaulay property of S divided by initial of I does not depend on the base field. And because of this statement, because we know that the initial is of König type as well, and initial is a monomial ideal. And here we had this statement. So we just apply these two things. So for any graded ideal, this ring, the Cohen-Macaulayness of this ring has nothing to do with the base field. Okay. Also, in the same paper that I mentioned in the first paper, we gave a description for Cohen-Macaulayness of the edge ideal of a König graph. In terms of some combinatorial information from the graph, I just will write down the statement. Let G be a König graph. As I told you, there are descriptions for the Cohen-Macaulay König graphs in the literature, but this characterization is different from the existing ones. So the combinatorial information from the graph, one of the invariants, I show it by alpha G, be the number of minimal vertex covers of G. Minimal vertex covers, say, D of G, such that cardinality of D is just the vertex cover number. And okay, we attach a graph G0 to G. Be a graph attached to G as follows. So I should explain what is G0. So whenever we have a König graph, we know that we have a matching number, we have a matching of maximum cardinality, which is just tau of G. Let, okay, E1 to be I1, J1, and up to EH, IH, and JH. Be a matching of G. Such that H is just the vertex cover number. This means that we choose a matching of the size of the, maximum possible cardinality. Then we consider G0 attached to G with vertex set. Just I choose from each of these edges one vertex. So the vertex set is just I1 up to IH. And two vertices from here, say IR and IS, we connect in G0 whenever the corresponding edges here, which are ER and ES, are connected in G. What does it mean two edges are connected in G? By this we mean that we have an edge from an endpoint of ER to an endpoint of ES. So if there is a third edge called E such that at the same time E intersection with ER is non-empty and E intersection with ES is non-empty, this means that these two edges are connected in G. So if this is the situation, we connect IR and IS in G0. So the statement says that then G is Cohen-Macaulay, which by this we mean that the ring S mod IG is Cohen-Macaulay if and only if simply alpha G is the cardinality of delta G0, and delta G0 is just the independence complex of G0. So the Cohen-Macaulay property is described in terms of two numbers which just can be read from the graph G. So this is the story about König graphs. I was going to talk about binomial edge ideals of König type, but now that I see the time, for sure I cannot do it in 15 minutes. So maybe I just explain. I don't write down, but I just explain you a little bit about binomial edge ideals. I just write down the definition of a binomial edge ideal. And I explain a little bit what we did. Then when you go to the paper, at least you have some idea what is inside. So whenever we have a graph G, we attach to this graph an ideal of this form. Okay, let me write it down more precise. So we have a graph G on the vertex set N. We consider the polynomial ring in two n variables, k of x1 up to xn and y1 up to xn. So this is the polynomial ring. Over it, this indeterminates. Now, what is Jg? It's just the ideal generated by such binomials such that I and j is an edge in G. Okay? So it's a binomial ideal whose generators correspond to the edges of the graph. This ideal was defined by Herzog and the other colleagues in a paper which is the beginning of the, a big study on this family of ideals. They are very well studied from different points of view. So we considered these kind of ideals and studied ideals of König type among this family. And the main result that we got in this context is that, first of all, these ideals are of König type whenever we have some nice subgraphs in the graph G, which we call them semi-passes. For example, if I have a graph like this, whenever I say a semi-pass, I mean a subgraph of this graph whose connected components are just pass graphs. For example, the subgraph generated by these three edges, you see that this is a pass of length 3, and also this one. So if I call this subgraph P1 and this P2, then P1 union P2 is a subgraph of this graph G whose components are pass graphs. What we showed is that an ideal JG is of König type whenever we have a semi-pass, which I mean such a graph, in G of length 2n minus d. By the length of a semi-pass, I mean the number of edges of the semi-pass. So here I have a semi-pass of length 4. Then this means that if I have a semi-pass in G of length 2n minus d, where d is just the dimension of S mod JG, okay? This just means that JG is of König type. So there is a nice description for those, for the binomial edge ideals of König type. And interesting is that if we consider this potential system of parameters that I introduced you in terms of the edges that come from a semi-pass, then this sequence is again a special system of parameters for JG. And then by the theorem that we proved at the beginning of this lecture, and we apply it once for monomial ideals, we can apply also this theorem to binomial edge ideals, and we get a corollary, which I just write down the statement. That's again the Cohen-Macaulay property of this ideal, also independent of the base field. So we consider a graph G such that JG is of König type. Then S mod JG admits a special system of parameters, and then this implies that the Cohen-Macaulay property of S mod JG is independent of the base field. Okay. This is the end of my lecture. Of course, as I told you, if you look at the references, you will see some, more results in this regard, but I'm out of time, so feel free, if you ask any question about this subject, you can write to me in this address, so.moradi@ilam.ac.ir. And okay, thank you very much for following, and wish you a nice day. Goodbye.